When astronomers spotted the strange object named Oumuamua passing through our solar system in 2017, the world was captivated. It was the first confirmed interstellar visitor, and it sparked debates about whether it was a comet, an asteroid, or even an alien probe. But now, a new discovery has shaken the scientific community once again. A second confirmed interstellar object, designated 3I Vatilas, has entered the spotlight, and it might hold even more secrets than Oumuamua. What is this mysterious traveler? Where did it come from? And most importantly, what does it mean for our understanding of life beyond Earth? Let us break it all down in 20 powerful points. The discovery of 3I Vatilas. The story of 3I Vatilas began with the ADLS Asteroid Terrestrial Impact Last Alert System project, a network of telescopes designed to detect potentially hazardous asteroids that could threaten Earth. In late 2024, astronomers using ATLAS detected a faint, fast-moving object cutting across the sky at an unusual trajectory. At first glance, it appeared to be just another comet, but the speed and direction did not align with ordinary solar system dynamics. Further analysis revealed that it was on a hyperbolic trajectory, meaning it was not bound to our Sun's gravity. This confirmed one astonishing fact: the object was an interstellar visitor, only the third of its kind ever detected after Oumuamua and Borisov. The object was given the official designation 3I Vatilas, with 3I, marking it as the third interstellar object confirmed in human history. Its detection was nothing short of a triumph for modern sky surveying technology, proving that with improved instruments, we are finally beginning to catch these rare cosmic travelers before they vanish into the depths of space again. How it differs from Oumuamua left scientists scratching their heads, because it behaved in ways no known asteroid or comet should. Its elongated shape, lack of a visible coma, and sudden acceleration away from the Sun led some to suggest it might even be artificial. In contrast, 3I Vatilas appears to behave more like a traditional comet. It has displayed a clear coma and tail, which strongly indicates the sublimation of ice and gas as it heats up while approaching the Sun. This makes it more straightforward to study compared to the baffling behavior of Oumuamua. However, its interstellar origin still makes it profoundly mysterious. Unlike typical comets born in our solar system's Oort cloud, 3I Vatilas comes from an entirely different star system. That means the dust, gas, and ices it carries could be samples of alien chemistry, untouched since the time of its formation. In a way, it is like receiving a delivery of raw material from a foreign world, giving us an unprecedented opportunity to compare our solar system's composition with that of another. This key difference makes 3I Vatilas perhaps even more scientifically valuable than its infamous predecessor. The interstellar trajectory. One of the most defining characteristics of interstellar visitors is their trajectory. Unlike objects bound to the Sun, which move in elliptical orbits, interstellar objects move on hyperbolic paths, a curve that ensures they will enter and leave our solar system without ever coming back. 3I Vatilas follows exactly such a path. Its incoming velocity, or hyperbolic excess speed, is far greater than any solar system object, confirming it cannot be native to our neighborhood. Astronomers have traced its approach vector back toward the constellation Serpens, though pinning down the exact star system of origin is nearly impossible. The vast timescales and distances involved mean that even a small gravitational nudge from another star millions of years ago could have altered its path before it drifted into our region. Still, what we can say for certain is that 3I Vatilas has likely been wandering through interstellar space for millions, if not billions, of years before its encounter with us. That fact alone makes it an extraordinary relic of the wider galaxy. A cosmic time capsule. What makes 3I Vatilas so intriguing is the idea that it might serve as a cosmic time capsule. Our solar system was formed about 4.6 billion years ago, but other star systems formed both before and after that. If 3I ATLAS originated from one of those systems, it could carry within it the chemical fingerprints of that system's early history. The dust and gases evaporating from it may reveal a chemistry slightly different, or perhaps radically different, from the familiar compounds we see in comets here. Scientists are particularly excited about the possibility of detecting organic molecules, which are the building blocks of life. Discovering organics on an interstellar object would suggest that the raw materials for life are not unique to our solar system but are scattered throughout the galaxy. That would strengthen the hypothesis of panspermia, the idea that life may spread from one star system to another via comets, asteroids, or other cosmic debris. 3I ATLAS could therefore hold vital clues about the very nature and origin of life itself. Why detection was so important. Detecting 3I's ATLAS early enough to study it properly is a major leap forward compared to Oumuamua. When Oumuamua was first spotted, it was already heading out of the solar system at incredible speed. By the time scientists realized its interstellar nature, it was too late to mount any kind of mission to study it up close. With 3I ATLAS, astronomers had the advantage of catching it earlier, giving them more time to observe it with telescopes and potentially even plan future spacecraft missions. The importance of early detection cannot be overstated. Interstellar objects are rare, but as our detection methods improve, we are realizing they may be more common than once thought. Being able to study them closely could revolutionize our understanding of planetary formation in other star systems. The discovery of 3I's ATLAS is a reminder of how much we still have to learn and how vital continued investment in sky surveys and telescope technology is for uncovering the hidden treasures of the cosmos. The peculiar shape of 3I ATLAS. When astronomers first attempted to determine the shape of 3I ATLAS, they immediately noticed that it was far from the standard spherical or elongated profile most comets and asteroids display. Observation suggested that the body could be irregular, tumbling in space in a way that made it difficult to pinpoint a definitive shape. This brought back eerie memories of Oumuamua, which was often described as cigar-shaped or even pancake, flat, sparking theories about artificial origins. For 3I ATLAS, the strange rotational light curves indicated that the object might be elongated, possibly hundreds of meters long, but with a chaotic spin that implies a violent history. Astronomers believe it may have been ejected from a star system after a planetary collision, which shattered and reshaped it before it was hurled into interstellar space. The lack of symmetry challenges standard models of cosmic debris. If it is truly that irregular, its aerodynamics during ejection and its survival through interstellar travel are almost miraculous. Scientists are now asking if such unusual shapes might be common in interstellar objects, or if we have just been extraordinarily lucky, or unlucky, in what we have detected so far. The shape alone adds fuel to speculation that 3I ATLAS is unlike anything in our solar system. Unexpected brightness variations. Another fascinating clue about 3I ATLAS comes from its inconsistent brightness. Unlike comets that gradually brighten as they approach the sun and shed material, 3I ATLAS displayed sudden fluctuations in brightness that did not correspond to its distance from the sun. At times, the object appeared to flare up without explanation, leading some astronomers to suggest that its surface might be highly reflective in patches, perhaps due to frozen ices or unusual mineral compositions. This irregularity could also indicate a fractured surface, where sunlight reflects differently depending on the angle. For others, it reignites the more speculative discussions. What if these changes are not natural but the product of reflective material deliberately engineered? Of course, mainstream scientists prefer natural explanations, such as volatile outgassing triggered by internal fractures, but none of the models perfectly align with what has been observed. The brightness shifts are not just scientifically puzzling, They are statistically rare among known comets and asteroids. This oddity strengthens the argument that interstellar objects might belong to an entirely different category of cosmic travelers, with compositions and behaviors we have yet to fully understand. Chemical composition. Clues of its origin. One of the most pressing questions about 3i is its chemical makeup. Astronomers know that by analyzing the light spectrum reflected from an object, they can determine the presence of certain elements and compounds. Early data suggests that 3i contains frozen gases and dust similar to comets within our solar system, but with subtle differences that hint at its alien origin. For instance, certain wavelengths indicate compounds rarely observed in our local neighborhood, raising questions about the star system it came from. If those compounds are confirmed, they could provide a fingerprint, pointing to the chemical environment of its birthplace, much like a cosmic DNA test. These findings could allow astronomers to compare its signature with the chemical compositions of distant star systems identified by telescopes like James Webb. Intriguingly, some researchers have speculated that the object might contain organic molecules, the building blocks of life. If true, this would lend weight to panspermia theories, the idea that life could be distributed across galaxies by interstellar bodies. Even without direct sampling, just knowing that alien organic chemistry exists elsewhere is revolutionary. 3i may therefore represent not only an alien traveler, but also a messenger carrying material from another world. The Tumbling Mystery. Unlike planets and moons that rotate with relative stability, 3i appears to be tumbling erratically through space. Its spin does not follow a smooth rotation, but instead seems chaotic, as though the object was violently ejected from its home system. This non-principal axis rotation is uncommon but not impossible. It usually occurs when a body suffers collisions or uneven outgassing that destabilize its spin. However, with 3i the tumbling seems unusually prolonged, raising questions about its internal structure. Is it a solid body, or is it more like a fragile rubble pile loosely held together by gravity? If it is the latter, its survival over millions or even billions of years of interstellar travel is extraordinary. The tumbling also complicates efforts to model its trajectory and predict how it will behave when interacting with solar radiation. Some theorists have even suggested that such tumbling could be consistent with a derelict spacecraft or an artificial construct that lost stability over time. While this remains speculative, the fact that 3i refuses to conform to expected behavior keeps astronomers debating late into the night. Its chaotic spin may be a key to unraveling its violent history. Energy anomalies in its trajectory. Perhaps the most unsettling finding so far relates to the subtle but measurable anomalies in 3i trajectory. Much like Oumuamua, it does not appear to follow a path dictated solely by gravity. Small deviations suggest an additional force is acting upon it, but scientists are struggling to define what that force might be. For a comet, such behavior could be explained by jets of gas pushing it slightly off course. Yet, in this case, the observed data does not perfectly align with that explanation, especially given the lack of a visible coma or tail at certain points of its journey. These anomalies have reignited speculation that we could be dealing with something more than just a wandering rock. Harvard astronomer Avi Loeb famously suggested that Oumuamua might have been propelled by light sails or other artificial means, and 3i seems to echo those same questions. Could this object be another technological relic adrift in the cosmos, or is there an unknown natural mechanism that we have yet to discover? Either way, the deviations from predicted paths make 3i a priority target for continued monitoring, as it might reveal a hidden side of interstellar physics. Or something far more extraordinary, the question of artificial origin. Whenever an object like 3i streaks through the solar system, the question of artificial origin arises almost immediately. With Oumuamua, the debate raged for years, with respected astrophysicists like A.V. Loeb suggesting that its unusual acceleration and shape might have been the result of intelligent design rather than natural cosmic processes. While most of the scientific community leaned toward natural explanations, the fact that serious voices even entertained the possibility shook public imagination. With 3i the discussion is beginning again, because any interstellar object that behaves unexpectedly opens the door to speculation. Could it be a piece of alien technology, a probe, or debris from some distant civilization? Scientists are careful not to leap to such conclusions, but they admit that if one wanted to disguise a spacecraft, it might look very much like a harmless rock. The sheer rarity of these visitors makes each one significant. Every piece of data collected on 3i could either strengthen the case for natural origins or reignite the firestorm of extraterrestrial hypotheses. The role of its highly unusual speed, one of the key pieces of data that scientists focus on when analyzing 3i is its speed. Interstellar objects do not move like the comets and asteroids bound to the sun. They carry with them the kinetic signature of their birth systems, shaped by gravitational slingshots from stars, planets, or even violent cosmic events. 3i is traveling at a speed far greater than the escape velocity of the solar system, confirming that it did not originate here. This hyperbolic trajectory ensures that it is just passing through, never to return. What fascinates researchers, however, is whether its speed can tell us about the environment it came from. If it was accelerated by the violent breakup of a planetary system, that might mean we are catching a glimpse of the chaotic processes of planet formation elsewhere. If, however, its velocity seems too stable and consistent, it might suggest ejection by gravitational interactions with massive stars or black holes. Every velocity calculation adds another layer to the mystery, transforming 3i from a simple rock into a messenger, carrying the scars of a distant and unseen birthplace. The mystery of its light signature. Light signatures are one of the most important clues astronomers have when studying distant objects. By carefully examining how light reflects off the surface of 3i scientists can estimate its shape, rotation, and surface composition. In the case of Oumuamua, strange flickering patterns suggested an elongated, cigar-like or pancake-like form, which was highly unusual compared to the mostly spherical comets and asteroids we know. With 3i early observations suggest irregular variations in brightness, which may mean it is tumbling chaotically through space. This could indicate that it endured a violent past, perhaps a catastrophic collision in its home system that sent it spinning out into the interstellar medium. Its color and reflectivity also raise questions. Does it have an icy, comet-like surface, or is it darker and more rock-based? These properties may determine whether the object is more akin to a frozen cometary fragment or an asteroid ripped from its parent world. Each shift in brightness recorded by telescopes across the globe is like a coded message, waiting to be deciphered by astronomers eager to unlock the story 3i is silently telling. Comparisons to interstellar dust streams. 3i is not the only thing flowing into our solar system from the stars. For decades, astronomers have tracked streams of interstellar dust, tiny particles from beyond the sun's reach, that constantly drift into our neighborhood. These minuscule visitors offer chemical insights into the makeup of distant star systems. But 3i is orders of magnitude larger and far rarer, making it an extraordinary find. Comparing its properties to what we know about interstellar dust is giving researchers new ways to calibrate their models. For example, is the composition of this large object consistent with the dust grains we already study, or does it tell a different story? If they align, it strengthens the theory that much of the galaxy is built from the same basic ingredients, recycled endlessly through star death and rebirth. But if 3i differs significantly, then it may represent a more exotic formation environment, perhaps around a type of star or planetary system unlike anything close to us. These comparisons highlight how unique large interstellar objects are and why each one represents a treasure trove of data far richer than any single dust particle ever could. The fleeting opportunity to study it, one of the most frustrating realities about interstellar visitors like 3i-ATLAS, is how fleeting the opportunity to study them is. Because of their immense speed and hyperbolic trajectories, they spend only a short time in observational range before disappearing forever into the vastness of space. With comets and asteroids native to the solar system, scientists have years or even centuries to prepare missions and make observations. With objects like 3i-ATLAS, the window is measured in weeks or months. Every telescope that can track it must be coordinated, and every instrument capable of capturing light signatures or spectra must be directed toward it before it is gone. Once it vanishes into interstellar space again, no second chance will ever come. This sense of urgency pushes astronomers to act quickly, pooling international resources to extract as much information as possible in the time available. The rarity of these opportunities makes them invaluable, because each interstellar object observed could hold unique clues about planetary systems scattered across the Milky Way. Missing one means losing a story that may never be told again. The role of 3i-ATLAS in understanding interstellar traffic. One of the most fascinating aspects of 3i-ATLAS is how it contributes to our understanding of the amount of interstellar traffic flowing through our solar system. Astronomers long assumed that space was mostly empty and that the chances of an object from another star system entering our own were extremely slim. Yet, in less than a decade, we have confirmed not one, but 3 interstellar visitors: Oumuamua, Borisov, and now ATLAS. This suggests that such interstellar objects are far more common than we once believed. If 3 have already been detected in a short period of time, how many others have passed through unnoticed over the centuries when humans lacked powerful telescopes? Scientists now speculate that our solar system may be continuously intersected by debris and objects from distant systems, some of which might even deliver organic materials or fragments of planets from other stars. This realization changes our perspective entirely. Instead of being isolated, the solar system may be constantly interacting with the galaxy at large, exchanging material in ways that could influence the spread of elements, and perhaps even life itself, across interstellar distances. Could 3i-ATLAS be artificial? Whenever an interstellar object like 3i-ATLAS is detected, one controversial but unavoidable question arises: could it be artificial? This idea was famously suggested by Harvard astronomer A.V. Loeb about Oumuamua, which exhibited strange acceleration patterns that could not be easily explained. While most scientists prefer natural explanations, the odd trajectories and unusual characteristics of these objects leave the door slightly open for speculation. With 3i-ATLAS, researchers are already considering whether there could be anomalies in its motion, rotation, or surface that might hint at something more than just a chunk of ice or rock. Could it be debris from an alien probe? Could it be a fragment of a destroyed megastructure drifting through the galaxy? While these ideas sound like science fiction, the truth is that with each interstellar visitor, we are reminded how little we know about what exists beyond our stellar neighborhood. Even if the odds are slim, the mere possibility keeps astronomers vigilant, carefully analyzing every detail in case an unexpected anomaly reveals something extraordinary. The importance of early detection. One of the biggest challenges with 3i-ATLAS and similar interstellar visitors is the speed at which they travel. By the time we spot them, they are already speeding past our solar system, giving scientists only a limited window to study them. For Oumuamua, detection came too late to send a spacecraft for close-up observation, and while Borisov was easier to analyze because of its comet-like activity, it still left the solar system quickly. ADOS is no different. It is fast, faint, and fleeting. This has renewed efforts among astronomers to develop better early warning systems. If we could detect interstellar objects earlier, we could potentially launch rapid response missions to intercept and study them up close. The payoff of such a mission could be enormous, providing humanity with a first-hand look at material from another star system. Such data might answer questions about how planetary systems form elsewhere in the galaxy, or even whether the building blocks of life are common beyond Earth. ADOS, despite its brief appearance, is helping fuel momentum for future technologies that could change how we study interstellar phenomena forever. What ADOS tells us about galactic evolution beyond its mysterious origin. ADOS also carries important clues about the broader story of galactic evolution. Every interstellar object is essentially a time capsule, holding within it fragments of the processes that shaped its home star system. By studying the composition, density, and trajectory of ADOS, scientists can learn about events such as planetary collisions, star formation, and even the violent ejections of material from young solar systems. These insights give us a small but powerful way to piece together how stars and planets across the Milky Way are born and destroyed. ADOS may also carry isotopic signatures or mineral compositions unlike anything seen in our solar system, broadening our catalog of cosmic chemistry. In essence, every interstellar traveler is like a galactic messenger, bringing a story from light years away. The study of ADOS, therefore, is not just about one object. It is about better understanding the billions of systems scattered across the galaxy, and by extension our own cosmic origins. Humanity's expanding role as cosmic observers. The discovery of ADOS underscores a turning point in humanity's role within the universe. For most of history, we were limited to observing the stars from afar, unable to detect or interact with objects from beyond our solar system. But now, with modern telescopes and advanced detection methods, we are beginning to witness the galaxy in motion. Objects like ADOS remind us that the solar system is not an isolated bubble, but part of a dynamic galactic environment filled with traveling debris, comets, and perhaps even technological relics. Each detection challenges us to expand our scientific curiosity and technological capabilities. It also forces us to confront profound questions: what else might be out there? Could these objects someday pose threats or opportunities for humanity? Will future generations be able to capture or even harness such visitors for exploration? ADOS is more than just an icy traveler.